I'm going to present the introduction, objective, and also the conclusion of this experiment at the end of the video. So first of all, we go to introduction. So this experiment was done to determine the loss coefficient, which is KL, and minor head loss, HL, M, and pipe components or fittings for different water flow rates, pipe diameters, and also different pipe bends. So in this experiment, we will have a few types of pipe section that will be used involving sudden enlargement and sudden contraction, bends, and also branches. Lastly, the value of KL for the fluid flows through a sudden expansion or enlargement and contraction can be obtained by considering the continuity equation of momentum and energy equations between 2 points. Next, the objective of this experiment is to calculate the minor head loss HLM and loss coefficient KL value for each of the pipe components or fittings. Number 2, to determine how different water flow rates, pipe diameters, and pipe bends would affect the value of loss coefficient KL. And lastly, to determine the factors that affect inaccuracy of the data obtained.
Assalamualaikum and hello everyone, my name is Adzin. Today I will present the theory part of this experiment. The flow in pipe system at the different flow rates may be required to pass through a variety of fittings, bends, or abrupt changes in area. Minor head loss HLM are additional head loss that occur mostly as a result of flow separation. As you guys can see on the slide, by simplifying the Bernoulli equation between 2 points for the horizontal elevation Z1 equals Z2, in the pipe, the pressure loss P and the total head loss HLT could be determined as follows, which is we can find by using equation number 5. The total between major head loss HL from the equation 3 and minor head loss HLM from the equation 4 can be used to find HLT. The value of loss coefficient KL is strongly dependent on the geometry of the component considered as well as the fluid properties that includes the Reynolds numbers RE and the mathematical function. This means the RE Reynolds number is big enough that inertia effects dominate the flow through that component, with viscous effects taking the second place. In this experiment, the loss coefficient KL and the minus head loss HLM value in the pipe for different flow rates, pipe diameters, and pipe bends will be determined. The first geometrical that will be tested is sudden expansion or enlargement and the sudden contraction. As you guys can see on the slide, the loss coefficient KL for sudden expansion or enlargement and the sudden contraction in the circular pipes or ducts are shown in the figure. Losses for the sudden expansion or enlargement and the sudden contraction are based on the speed. Consider the continuity equation number 7, momentum equation number 8, and energy equation between points number 1 and 2 from the equation number 1 from the previous slide for the control volume to get value of loss coefficient KL for the fluid flows through a sudden expansion or enlargement and sudden contraction. Next, the geometrical that will be tested are elbows, pipe bends, and pipe branch. By using equation number 3 until equation number 5, the value of minor head loss HLM and loss coefficient KL for flow containing pipe component or fittings like elbows, pipe bends, and pipe branch might be found experimentally. As you guys can see on the slide, the figure is an example of typical value of loss coefficient KL for pipe component or fittings. That's all from me. Thank you. I will pass to the next presenter.
Assalamualaikum, I'm Afika. I'll present about the apparatus and methodology. So the apparatus for the experiment is tested pipe section, inlet valve, outlet valve, 2 tube manometer and manometer tube. First of all, the direction of water inflow and outflow are determined for the tested pipe section. Second, inlet valve for tested pipe section was fully opened by turning it to anti-clockwise direction, while inlet valve for non-tested pipe section was closed by turning it to clockwise direction. Next, pump was turned on and the outlet valve was slowly opened until fully opened by turning it to anti-clockwise direction, and wait for a while in order to remove any air bubbles for the tested pipe section. The inlet flowing pressure H1 and the outlet flowing pressure H2 were identified for the tested pipe section, and the manometer tubes from those H1 and H2 of the tested pipe section were connected to the two tube manometer, H1 inlet and H2 outlet. Next, the value of H1 and H2 in millimeter at 2 tube manometer were recorded. Next, the actual water flow rate QX was determined by recording the time taken to collect the 3 liters volume of water at the tank. The opening of outlet valve was reduced, and step 4 and 5 was repeated for 5 different values of QX. The manometer tubes were firstly removed to avoid the bubble in the tube after finish. Step 1 to 5 for the other tested pipe section were repeated with pump in running condition. All the manometer tubes from the system were removed after finish. Inlet and outlet valve were fully closed. Main switch and pump were turned off.
Hello everyone, I am Chua and I will continue the presentation with the data. The first one is about the started instrument with the outer diameter of 30 mm, thickness 1.5 mm, length 135 mm, outer diameter 32 mm, and thickness 1.8 mm. The water volume that we use are fixed with 3 liter, 2 liter, 1.8 liter, 1.5 liter, and 1 liter. For example, the time used to correct 3 liter water is 4.25 seconds, and the H1 is 39 mm, the H2 is 43 mm. By dividing the volume with the time, we can get the flow rate which is 0.7059 liter per second. And by minus the H1 with the H2, we can get the difference of H which is the negative 0.004 meter. Then we can minus the outer diameter with the thickness to get the inner diameter. Then calculate the area with the formula of diameter square times with pi divided by 4, and the A1 for the area 1 for the southern experiment is 0.0002701 meter square. After that, we also can total the 5 flow rate and divide with 5 to calculate the Q average, which is 0.0006105 meter square per second. After that, we just repeating all the steps with another information, we can get the whole data. And the slide show the data of the sudden experiment and the sudden contraction. So the following is the data information for the 2 angle 90-degree pipe, 2 bend 90-degree pipe, 2 angle 45-degree pipe, Y-type pipe, and T-type pipe. By the way, due to all the diameter of this pipe are same, the area for 5 pipe are 0.0022701 meter square. The steps are repeating and the average of the flow rate are calculated.
Hello, my name is Ahmad Zikri and I will present to you the discussion of this experiment. So for the first discussion, calculate the minor head loss and loss coefficient for each of the pipe components or fittings. Note for the major losses calculation, set the temperature of flowing medium equals to 36 degrees Celsius and determine the coefficient of friction by using Blasius formula. So first we need to find the loss coefficient. So the loss coefficient KL is equals to 1 over A1/A2 square in bracket square. So to find the area, we need to find the diameter first. It is given at the table, the outer diameter D1 and D2, outer diameter of D1 and outer diameter of D2. So we need to find the inner diameter, so we minus the thickness of the pipe, so thus we can find the D1 and D2. From D1 and D2 we can also find the area A1 and A2. So from there we can find the loss coefficient KL, and it is the unit is dimensionless. So okay, for to find the major to find the major to find the Blasius formula, it needs to find the Reynolds number. So the Reynolds number is equals to velocity times diameter over viscosity. So the viscosity, it is stated that the temperature of the flowing medium is 36 degrees Celsius. So the viscosity for that medium is 7.1 E negative 7 meter square per second. So okay, so for velocity, it is from the table is just given the flow rate, so we need to find the average for it, and we need to change the unit from liter per second to meter cubic per second. So from there we can find the velocity by using the formula V is equals to Q over A, and we use A1. So from there we can find the velocity, and the diameter is already given, we use the D1. So so from there we can find the Reynolds number, and from finding Reynolds number we can find the coefficient friction by using the Blasius formula, which is F equals to 0.316 over 4 root of Reynolds number. So it is also stated to find the minor head loss. The minor head loss, the formula is KL times V square over 2G over 2G. So the KL we have calculate, and also the V and the 2G G is constant. So from there we can find the minor head loss in meter. And also for the major head loss, we use the formula FLV square over D2G. So all the information has been calculated, so we just transfer it to the formula. So from there we can find the major head loss as well. And for the sudden contraction, we repeat the exact same step, but using the information from the data given. Okay, so for the table 2, we use 3 types of component or slash fittings. So for the first component, we use 2 times angle 90. So so the step just is the same as the previous table. We find the diameter and then the area, but the KL it is already constant from the table, from the figure 3 at the lab manual. So for the angle 90, the loss coefficient is 1.5, but it has 2, so the loss coefficient needs to time 2, so 1.5 times 2 equals to 3. And then for the rest, we calculate as same as before. So for the second component, we use bent 2 times bent 90. Same, the calculation and the steps are same, but the loss coefficient for this component is 0.7, but it needs to times 2, so the loss coefficient is 1.4. So for the third component, it is the 2 times angle 45 degree, same steps and same step. So but the loss coefficient is 0.4, and it needs to times by 2, so the total loss coefficient is 0.8, and the steps are same, so just calculate like the previous one. Okay, so for table 3, the calculation and the step are the same as the previous one, except the KL is different. So for the first component at table 3, which is the Y type, the loss coefficient here is 2. So we use the same steps to do the calculation. And also for the second component for table 3, which is the T type, the loss coefficient is also 2. So proceed to do the same calculation steps. So that's all for the first discussion. Okay, so for the discussion number 2, discuss the effects of different water flow rates, pipe diameters, and pipe bends on the value of loss coefficient KL. So it is given that the minor head loss is HLM is equals to KL V square over 2G. So to find the relations between the water flow rates, pipe diameters, and pipe bends to the loss coefficient, we just use the formula KL is equals to 2G times minor head loss over a V square. So from V we can find the area of the pipe and the water flow rate of the pipe by using the formula V is equals to Q over A, sorry. V is equals to Q over A. So from there, the formula is, we can do the relations by using the formula KL is equals to 2G times HLM, minor head loss, times A square over Q square. So if the so the higher the water flow rates, so the lower the loss coefficient of friction, and then for the pipe diameter, if the pipe diameter is larger, then the loss coefficient of friction is also larger. And then for the pipe bend, if the pipe bend is 90 degrees Celsius, the loss coefficient of friction will be higher. But if the pipe bend is 45 degrees Celsius, the loss of coefficient will be lower than the 90 degrees Celsius. And also if the pipe bend is 180 degrees Celsius, which is straight line, which is a straight pipe, then the loss coefficient will be the lowest. Okay, so for the third discussion, briefly discuss on factors contributing to errors or inaccuracy in experimental data, and the possible recommendations to improve the existing results. So for the first errors, parallax error could be occur during the reading of H1 and H2 at manometer tubes. So to to fix this problem, we need to ensure that the position of the eye is perpendicular to the reading scale of the apparatus. So for the second error, instrumental error could occur at the pipes, where the pipes could be leaking, which will affect the water flow rate, loss coefficient friction, and minor head loss. So to overcome this problem, we need to check first if there are any damage to the apparatus before conducting the experiment. And for the last error, the water level in the manometers cannot be calibrated and fluctuates heavily. So we need to avoid that, we need to adjust the volumetric flow until it does not fluctuate or take the average reading. So that's all for the discussion part. Thank you.
As a conclusion, the value of the minor head loss HLM and loss coefficient KL for each of the pipe components or fittings was successfully obtained. Minor head losses occur at any location in a pipe system where streamlines are not straight, such as at pipe junctions, bends, valve contractions, expansions, and also at reservoir inlets and outlets. So the loss coefficient of friction, F, is inversely proportional to the water flow rates, but it is proportional to the pipe diameters. Lastly, they also have some errors in this experiment, such as systematic error and random error.